Hi, welcome to another Math 9 video. Today we're going to be looking at 7.2, inductive reasoning to find the nth term. And we're going to start off with these diagrams. And I'm going to say that n, which we've seen in the past, is our figure number. So here I'd have n equals 1, n equals 2, and n equals 3. That's referring to the figure number that we're dealing with. And we're trying to figure out if I were to keep this going, and I had an nth figure, so third, fourth, fifth, all the way up to nth, I would want to come up with an equation for how I would determine the number of squares that I have. So, how we would do that, if we take a look at this, if I'm counting the number of squares, maybe a nice approach is to count how many I have. I look at it in terms of dimension. So how many I have going up times how many I have going across. So that would give me 2 times 3 for this first one. And from that I would get 6. In the next one I'd have 1, 2, 3 times 1, 2, 3, 4. So you're starting to see the pattern of what we're working with. The next one, that would be equal to 12. And then 1, 2, 3, 4 times 1, 2, 3, 4, 5 at the bottom. So 4 times 5, and I would get 20 for this one. So I'm trying to use this pattern to come up with what it might be for some nth pattern way further down the road. And that nth could represent anything. It could be a 100th pattern, it could be the 50th pattern, it could be the 50th figure, it could be the 20th figure. But I want to come up with an equation so that I could use it for any figure number that I'm interested in. So I'm looking at the relationship. This is not like how it was last day where it's a linear relationship. So if I look at this, this is going up by 6. And if I look at this, this is going up by plus 8. So it's not a linear relationship where I have the same common difference in between them. That's when I know I'm probably looking at multiplication. So I'm looking to multiply 2 values together to come up with what my new solution would be for the number of squares in the diagram. So I in order to try to come up with that, if my figure number here is 1, I want to relate this and think of it in terms of its relationship to the figure number. So for this first one, my figure number is 1, but the first number I'm multiplying is 2. That would be like saying n plus 1, because my n in that case is 1. So 1 plus 1 gives me 2, so that works. And 3, the relationship to that would be n plus 2. So in this case, my n value is 1. That would be saying 1 plus 1 times 1 plus 2, which really is 2 times 3, and it really works out to be what I got for my value there. Now I want to test it out with this next one to see if my figure number here is 2, does my equation, which I'm going to put a box around here, let's test it. Does it work here? So if it's n plus 1, the n in this case is 2, so it would be 2 plus 1, times n plus 2, so it would be 2 plus 2. So this means it's 3 times 4, which really does give me 12, so I can say yes, this formula works. And I'm going to test it one more time with this last one. N plus 1, well, the n here is 3, so 3 plus 1, times n plus 2, so 3 plus 2, so that would be 4 times 5. So 20 is what I should get, and it really does work. So after all of that, determine an equation. Well, it would be n plus 1 times n plus 2 would be my equation. So this is a little bit different than what we did last day, because last day we were looking at linear patterns where they had a common difference in between them. This time we're looking at multiplication, and we want to relate the formula or equation back to the original figure number that we're working with. Okay, so let's use a similar idea without diagrams this time. I just have a set of numbers, but I want to try to come up with a similar type of expression. I always start with this. I check to see what's the difference between these, because if it's the same, then I know what to do with this. This is plus 3. This is also plus 3. And this is also plus 3. So that's like my common difference. So I can say 3 times the figure number or the term number. So that would be the first term, that'd be the second one, that'd be the third one, and that would be the fourth one. 3 times that, and then I'm going to put some dots here because I want to figure out what I do after multiplying by 3. So in the first example, I would do 3 times 1, but then to figure out the dots, I know that I end up at 6. So I'm thinking to myself, okay, I get 3 here. 3 plus 3 is going to give me 6. So that works for my first one. Now I want to test it for term 2, or where I have my n equals 2, and I would test it like this. It would have 3, so I'm thinking this might be 3n plus 3 might be my formula. Let's test it. 3 times 2 plus 3. If I'm correct, this should give me the number 9, which I see up here. So 3 times 2 is 6. Plus 3 really does give me 9, so I can say that this is definitely my formula, and it works. Okay, so moving on to the next one, we always check to see if I go here to here, it's plus 3, here to here is plus 5. So I can see that this is not, this would be plus 7, and on. So it doesn't follow a linear pattern. It doesn't have the same number that's being added each time. So I'm thinking this must be something to do with multiplication. So I'm thinking of multiplication to figure out my nth term. So if n, or my term number here, would be 1, I'm going to circle them. This one would be 2. This one would be 3, this one would be term 4, term 5, term 6, and I'm wanting to figure out what it would be for term n. So let's try to figure out the pattern. If we're dealing this time with multiplication, okay, we're trying to figure out how we can multiply to come up with these different values. So let's start with that 0 first. So I'm thinking, what times what gives me this value? Okay, I could say like 0 times 1 or 0 times 2. The next one would be 3, and I'm trying to come up with how I would get that. This would be 1 times 3. And if I get to 8, I'm following the pattern I see here, 0, 1, I could do 2 times 4. And if I carry on, the next one would be 15, and I could say that's 3 times 5. So how did I think to do these? Well, maybe the first thing I started with is like the number 3 is a prime number. The only numbers that could multiply to give me that are 1 and 3. So I wanted to use 1 and 3 there and then find some pattern that follows that with the other values. We could keep this going, but maybe we can just stop there. And so the relationship between this and the figure number, well, if this was for figure n equals 1, my first value here would be like saying n minus 1. And this value here would be like saying n plus 1. Let me see if that also works here. N, this is figure number 2, so n minus 1 would be 1, and n plus 1 would be 3, so it works in this case. So I want to double check. 15 was my fourth term. So let's check our fourth term, or in brackets I'm going to say n equals 4. So let's check that right here. if my formula really works, well, it should be 4 minus 1 times 4 plus 1. 4 minus 1 is 3. 4 plus 1 is 5. So if this is true, I should get the number 15, which is what I got here. So I know that this formula really does work. So this is what I would give as my solution. Okay, so let's try one more example that resembles this, because I get that these are a little bit tough or a little bit different than what we've done before. So let's first of all always start by checking to see, does this have a linear pattern? Does it go up by the same common difference every time? So if I go here, I would do plus 4. But if I go here, it's plus 6. If I go here, it's plus 8. Okay, so I do see a pattern. Each time the amount I add goes up by another 2. So plus 4, plus 6, plus 8, plus 10. But that's not a linear pattern because it's not a common difference. The difference is changing each time. That's how I know it's got to be something times something to come up with that value. So I'm going to get rid of this so that I can write my term number for you. So here, this term number would be, that would be the first term. This would be the second term. I'm going to circle them so we don't get confused. That's the third term, fourth term, fifth term, on, and eventually we would want the nth term. And we want to come up with a formula again for the nth term. So to help me to figure it out, I'm going to look at the factors of this. So the 2 is again a prime number, so only 1 times 2 could give me an answer of 2. And then for 6, I could do 1 times 6, but it's not a prime number, so I probably don't want to use that one. I would go up 1 because we're always looking for a pattern of increase. So 2 times 3 would give me 6. The next one, 3 times 4 would give me 12. And this one we know is 4 times 5. So we can start to see, and I'm going to stop there, but we can start to see a pattern that's forming. And we're trying to link the figure number with these values here. Like we're looking at it and thinking, do they have some sort of connection? So if the figure number is 1, the first number I'm starting with here is 1. The figure number is 2, I'm starting with 2. Figure number is 3, I'm starting with 3. So I'm thinking the first part of my equation is just n. So whatever the figure number is, that's the number I start multiplying by. Then I would multiply that by n plus 1, because as I can see here, it's 1 times 2, 2 times 3, 3 times 4. So I'm always multiplying by one number larger than what the figure number is. So I think this is our formula, but I want to be certain, so maybe I'm going to check this out with figure number, let's test 5. So according to this, in figure number 5, I should have 5, because that's my n value, times n plus 1. So that would be times 5 plus 1, which is saying multiply 5 by 6. And so my fifth figure should be 30. And that is what it is here. So I can say, yes, this definitely is my solution. Okay, now looking at just a couple of new concepts. We're looking at counterexample, not consistent with a general statement, and it may be used as an argument against it. You'll often see this in debates, but we also can use this in math to show a statement is not true. So, for example, here's how this shows up in math. All fractions are less than 1. Okay, so that is true if we have something like 1 over 2 or 1 over 5. But are there fractions that could be more than 1? Yes, there definitely are, so I don't agree with this statement. So I would say my counter example would be, well, I could write it in words, or you can even show me using an example, But what I think of is, how about the fraction 3 over 2? Is that a fraction? Yes, it is. What would it be equal to if let's say I change that to a decimal? It would be 1.5. Or I could say 1.5 means the same thing, but those are both bigger than 1. So I have used my counterexample to disprove the statement. Okay, the next one is multiplying two numbers always results in a larger number. That is often true. It's true, I would say, most of the time with the values we work with, but I can think of a counterexample. So I am trying to come up with one example to try to show that this is not true. So how does this come up using math? Well, one example I can think of is multiplying by 0. 9 times 0, those two are numbers, so I'm following the rules here. It's saying it always results in a larger number. Well, no, the answer to this is 0. So I could give this as a counterexample, and that would be perfectly fine. I'm just going to give you another one. Actually, I'm going to give you another two, and you could provide me with any one of these, but also if we have a negative, let's say we do negative 3 times 4, okay, it always results in a larger number. Well, no, the answer to this is negative 12, which is actually smaller. And one last example of this is, what if we took 1/2 and we multiplied it by 1/2? Whenever we multiply fractions like this together, the numerator is 1. The answer in the numerator is still 1, but the denominator gets larger, so 2 times 2 is 4. So if we think logically about this, a quarter is smaller than a half. So you get to see that example of a counterexample. So here's your assignment, and that's the end of this video.